Well, hello everyone. I think you can hear me now. So hello everyone, welcome to this fireside chat entitled The Earth Observed by the Machines. My name is Pedram Gamisi and I work as the group leader of AI for RS at the Institute of Advanced Research in Artificial Intelligence, or IRA in short, which is located in Vienna. I also work as the head of the machine learning group at AZDR HIF, which is located in Germany. Well, machine learning for Earth observation or remote sensing is a mature field of research. For example, advanced machine learning techniques have been developed and utilized for a variety of applications, such as urban management and developments, land use and land cover mapping, forest-related applications, crop monitoring, climatology, environmental mapping, and so on. Well, what is remote sensing or RS? What is Earth observation or EO? I'll talk about them later on in these fireside chats. Well, the main purpose of this chat is to investigate some of the challenges existing in the field of Earth observation and explore how AI and EO can help each other to address these challenges. Well, before starting the chat, I would like to introduce our guests, Naoto Yokoya, Ronnie Hensch, and Fabio Pacivici. Well, Naoto works as a lecturer at the University of Tokyo. He's also a unit leader at the Riken Center for Advanced Intelligence Project, which is located in Tokyo. Naoto was the previous chair of the IEEE Geoscience and Remote Sensing Society Image Analysis and Data Fusion Technical Committee. His research interests include image processing, data fusion, and machine learning for understanding remote sensing images with applications to disaster management and environmental monitoring. Ronnie works as a research scientist at German Aerospace Center, or DLR. He is now the chair of IEEE GRSS Image Analysis and Data Fusion Technical Committee. His research interests focus on ensemble methods and deep learning for the analysis of remote sensing images with a focus on synthetic aperture radar, which is a particular type of data set which is used mostly in the remote sensing community. Fabio works as a distinguished scientist at Maxar Technologies. He has 15 years of experience in developing innovative geospatial products with the vision of bringing together the advancements in the satellite industry with the computer vision and artificial intelligence research communities. Well, he serves as the VP of Technical Activities at IEEE Geoscience and Remote Sensing Society. Well, I think I can share my slides now. And hopefully you can see my slides. Well, in this chat, we will give a short introduction to remote sensing and some of its challenges, where a tight synergy between RS and AI can offer solutions. We will then discuss a few differences between computer vision, or to be exact, close-range computer vision and Earth observation tasks. And we also mentioned why most of successful approaches in computer vision cannot be directly applied to remote sensing data. In addition, we discuss how a strong synergy between industry, academia, and government agencies can better serve the broader remote sensing and AI community. Well, let me start with a brief introduction, and after that, Ronnie, Naoto, and Fabio will give short talks about different aspects of EO and AI, respectively. Okay. What is AI for EO? Well, this fireside chat is co-hosted by IRA and IEEE GRSS at ICML. So I believe you have a very good understanding of AI. So here I would like to focus a bit more on the EO part. What is EO, or what is remote sensing? The United States Geological Survey, or USGS in short, defines remote sensing as a process of detecting and monitoring the physical characteristics of an area by measuring its reflected and emitted radiation from a distance. Well, these can be done using spatial cameras or sensors that are mounted on different platforms, such as airborne platforms, spaceborne platforms, or for example, drones. These spatial cameras or sensors capture remotely sensed images or data sets from the immediate or almost immediate surface of the Earth. And then researchers like you, researchers like me, will sense, process and analyze these data sets and sense things about the Earth. Well, to process these multi-sensor and heterogeneous data sets, we can make the most of advanced AI techniques, and this shapes the backbone of AI for EO. Well, as its name says, AI for EO is an interdisciplinary field of research. In my opinion, if we want to do something out of the box, we need to do interdisciplinary research works. For example, in the AI community, people are developing very sophisticated approaches. On the other hand, in the EO community, people are dealing with lots of complex scenarios, complex challenges and issues. So a good synergy between these two communities can solve some of the most challenging issues in this world, such as global warming and climate change. Or at least they can offer some good solutions to partially address those problems. Okay, we are now in the era of massive data acquisition. In the field of remote sensing, the number of platforms for producing remotely sensed data has sharply increased. This has been coupled with the use of new platforms for proximate sensing, such as unmanned aerial vehicles or UAVs, producing very fine spatial resolution data. Therefore, we have different sensor types mounted on different platforms, such as airborne, spaceborne, and UAVs. So such heterogeneous, large-scale data sets can provide complementary information from a particular scene located on the immediate surface of the Earth. And then we can use, for example, we can develop different types of multi-source data fusion approaches to make the most of these data sets with complementary information. Well, so far, so good. We have a huge amount of challenging data sets. We have a huge amount of large-scale heterogeneous and high-dimensional data sets. And that are freely available for researchers. But and this is exactly what we need in vision communities. But there is a fundamental issue here. The number of labeled training samples is doomed to remain small, while the amount of data is huge. Why? Because the collection of labeled data in remote sensing is either time-consuming or expensive, and it can also be dangerous since labeled data collections sometimes require field works in more complex and remote areas. And this is one of the main reasons why many deep learning-based approaches cannot be simply adopted for remote sensing images. Well, Ronnie will talk about these differences in more detail later on, right after my short introduction. So in my opinion, this is the most challenging methodological issue in the remote sensing community. Of course, we are dealing with a lot of challenges, but from the methodological side, in my opinion, this is the most challenging issues. The amount of data, the amount of high dimensional, large scale and heterogeneous data sets are exponentially increasing, but at the same time, we only have a limited number of high quality labeled samples. Well, there are two general solutions for this problem. We can either invest more and more on field campaigns or label data collections to produce high quality training samples, or we can invest more on let's call them no supervised approaches. And when I say no supervised approaches, I'm referring to a variety of approaches, including unsupervised approaches, semi-supervised approaches, few-shot learning, or weakly supervised learning. For example, I put an example here. The first row here shows Earth observation data. The second row shows low quality, inexact, inaccurate, and noisy labels, which need to be used to train our algorithms. And the third row here shows the output classification maps that we produce using these low quality training samples. And this shapes the general idea behind weakly supervised approaches. Well, specifically related to weakly supervised approaches, we organized a couple of events and activities in the remote sensing community in 2020 and 2021. together with our partners at Technical University of Munich and Microsoft. And Naoto will talk about these events, which are specifically related to visually supervised learning in more detail later on. Well, here I'm done with the introduction part, and I think without any further ado, we can proceed with the next presentation, which is going to be given by Ronnie. But in the meantime, please don't hesitate to post your questions through the chat box that you can find in your Zoom. I'll sort them, and we will answer all those questions in between all the presentations or right after all the presentations. Thank you. Ronnie, the stage is yours.
Yeah, thanks, Petran, for this nice introduction before, and also for this perfect introduction to my part of the chat. So I hope you can hear me well and also see my slides now. So I would like to use this time to talk a little bit about the differences between remote sensing data and computer vision data. And well, computer vision data, I mean something like, images acquired usually by digital cameras at a near range. So here you see two examples. On the left-hand side, there is the typical remote sensing data set. It's a multispectral LiDAR with the corresponding semantic segmentation. So pixels assigned to each of the labels assigned to each of the pixels. And on the right-hand side, you see a typical image from the Microsoft COCO benchmark data set. So what is the differences between those two different worlds? Well, one thing is that the sensors we are using in close-range computer vision, well, they are more intuitive for us to interpret. And the reason is that it's dominated by digital cameras, right? Color cameras. So they are designed in a way to match the human visual system. So they have those three color channels, the same as the human eye. Green is dominant because the human visual system is very sensitive to green. There's a tone mapping involved in the processing of those images, which aims to produce images that are visually pleasing to humans. So it's very easy for us to interpret those images because those images are designed to be very close to what we experience in daily life. On the other hand, for remote sensing, it's much closer to actually like a physical measurement of the Earth. So for example, we might have very uncommon image geometries. The eye, as well as a digital camera, is usually like measuring an angle of the scene. So, where a certain object lands on the picture is depending on the angle between the area of receptors, either camera or eye, and the angle between to the object. While for synthetic aperture radar, for example, it's more a distance measurement, and this has certain effects like a layover. So here you see the same building. What you also see here, this is a scene from Berlin. So this building is basically falling towards the sensor because SAR is rather measuring the distance, which makes it very hard, even for experts, to analyze this and interpret this kind of data. Another thing is that in remote sensing, we have very different measurements. So SAR, synthetic aperture radar, is, for example, measuring the amplitude and the phase of a microwave pulse that is backscattered on the ground. For hyperspectral images, we have hundreds of very narrow spectral bands where we're measuring the light intensity. While in close-range computer vision, well, we have those three colors that we are used to, right, when we look at the visual system of mammals, for example. Another difference is data availability. For close-range computer vision, if I want to have example images of a certain object, usually one thing you can do, and in most of the cases, is you just go into the internet and you make an image search, right? There you will find easily thousands up to millions of images, to some extent already labeled because you can search for this specific object. Now for remote sensing data, the situation is much, much different, right? So here, the images are acquired by satellites. This data is usually not free. Or by airborne sensors, where it's very often also not free. The situation is getting a little bit better. So there is now the Copernicus program, for example, that is making the data of European satellites at least the Sentinel constellation free to the public. For another satellite, you can just like write a science proposal and then you still get the data. But still, I mean, it's much harder to get this data than for like close range computer vision problems. Another problem is standardization. So in close range computer vision, I mean, we do have like PNG or TIFF images, in the worst case JPEG images, right? So it's very clear what is the data format there. In remote sensing, that is less the case. So usually every kind of sensor, every kind of satellite is coming with its own data format, right? So this also means that you need to have different loaders, different visualization techniques, different pre-processing techniques, and so on for each and every of the different sensors that we have. And the biggest problem, and that was already mentioned by Petram, is the labels, right? So now for machine learning in general, but now with deep learning, what we need is labels. And well, in close range computer vision, what you can do, what is heavily done, is you use layman's to label your images. And this is possible, right? So you can use crowdsourcing, for example, you send your images to Amazon Mechanical Turk or whatever crowdsourcing platform you want to use. And the layman's can label those images to a certain extent because they correspond to like daily objects, like there's a car, there's a person, there's a certain kind of animal in this image. So this is something nearly everybody can do. In remote sensing, it's harder. So if you talk about optical remote sensing images, then maybe people still can do that. But if you talk about radar images or spectral images, you need expert knowledge in order to really do this. And very, very often, even as an expert, by looking at the data, you can't label it. When we talk, for example, about geophysical properties of the ground, like soil moisture, you can't look at an image and as an expert say, this image, this part of the ground has a certain soil moisture. It's just not working. So for this, you would need to have in situ measurements. This means you actually need to go to this place and measure it there. Another difference is that in close range computer vision, we usually have like thing classes, like objects. There's a person, there's a certain type of animal. And for this kind of classes, what you can use are part-based models, right? That was very successful in computer vision for a long time. Now, in remote sensing, we rather deal with stuff classes. So we also have objects like airplane detection or ship detection or car detection, but mostly we deal with stuff classes. So things that are just like spread out in arbitrary shapes. So here, part-based models or shape-based models are completely useless. There is no common shape of a forest or something like this. So those approaches simply won't work. And the other problem we have is that in close-range computer vision, since we are mostly dealing with objects, the labels are quite clear and discrete. A cat is a cat, right? So this part of the image belongs to a cat and another part does not belong to a cat. For remote sensing, the labels, well, the classes we are dealing with, they are much more continuous. So is this image here on the left-hand side, is this a forest or a road? Well, it's showing kind of both, but how would you label it? Same on the other hand. So there's a couple of single trees. So probably this one you would not call a forest anymore, but this here in the middle, maybe yes. So it's much harder to really assign a single label to this kind of image data. And this also, one other reason for this is that the classes we are dealing with, they're much more ambiguous. So when we talk about road, for example, is the parking lot in front of a supermarket. Does it belong to the class of road? What about the runway of an airport? What about a dirt path through an agricultural field? So it's much less clear what actually belongs to a specific semantic class we might want to define. Another difference is resolution. In close-range computer vision, we have usually high-resolution data with a couple of exceptions. So much so that one of the most common pre-processing steps for many computer vision pipelines is actually to downscale your images, because we do not need to have this high resolution in order to make the decisions we're interested in. In remote sensing, it's the other way around. So here, especially when we talk about spaceborne sensors, the resolution is usually lower than we would like to. So there's a lot of effort in upscaling the images to a higher resolution. And same is also true for the reference data that we have. So very often the reference data, like in this case, the semantic maps, but also other things like geophysical properties, and they are integrated over a larger area, leading to a very coarse resolution map of our target variables. All right, so this sounds like, remote sensing only has kind of like disadvantages, but of course there are also a couple of things that makes it a little bit easier in contrast to computer vision. One thing is object scale. For computer vision, you basically don't know the scale of the object. The distance between your sensor and the object is arbitrary. It can be very far away, it can be also very close. And this is introducing a lot of change in the appearance of your objects. For remote sensing, usually the object scale is fixed because you do know the distance between the object and the sensor, right? So satellites fly in a certain orbit, planes follow a certain flight path. So you do more or less know the distance, and this is the object scale. And the other difference is that for remote sensing, since we are closer to the actual physical measurement, we very often have physical models that are linking our observables with the target variables we have in mind. In particular, when we talk about geophysical properties. So those models can be used in order to constrain the solutions you want to find with machine learning, for example, as a regularization term, for example, or just like restricting the solution space of a neural network or something like this. So those differences lead to a couple of a couple of challenges. So the first thing is that our data sets are very small, very often just a single image. This is getting better and better, so there are more and more data sets that are larger than that, but a lot of research is done still on a very small data sets that does not cover all the data variations you might see in practice. So self-supervised learning and domain adaptation, transfer learning is very, very important in remote sensing, much more than in computer vision maybe. Then we have a very strong spatial correlation because our objects are very big and homogeneous in the images, both in appearance, but also in semantic meaning. And the other thing is we have really a significant amount of label noise when we work with outdated maps, for example, or misalignment issues, but also if we have human experts labeling that, because as I mentioned before, the definition of the classes is much more unclear. So here you see like 4 people try to label road. If they agreed on the label, it's red. So then four of the labelers agreed that this is a road. If it's a different color, then they disagreed, right? So it's usually, as I said before, parking lots, the runway of an airport, and one person even labeled like a railway as part of the road network. And last but not least, we have very imbalanced label distributions because for Earth observations, some classes appear just much more often than other classes, right? They are just rarer than, I don't know, urban areas, for example. And this is something we always have to deal with. So all of this makes remote sensing a very exciting research field with a lot of challenges that can be solved with machine learning. And I think that that's why you're here and what we want to talk about. All right, and with this, I'm at the end, and we can continue with the next speaker.
Thank you very much, Ronnie. Thanks a lot. There are a couple of questions. Maybe we can read them out and answer some of those questions, and maybe we can answer all of those questions right after all the presentations. Well, one of the questions is, I'm interested in approaches regarding limited high quality samples and strategies to overcome this. What would be a good place to start? Right after Ronnie, Naoto will talk about some of the activities that we organize related to weakly supervised approaches. Maybe you can get your answer there. Otherwise, we can surely discuss these in more detail right after all the presentations. Well, So asks, if data for remote sensing is hard to acquire, is there demand in studying methods to plan where to acquire data such that optimal amount of information is gained?
Yeah, so just to clarify, the data itself is not so hard to acquire. There are more and more satellite missions. There's now a lot of airborne sensors available, even drones that are getting more and more affordable. So acquiring the data is not so much the issue. What is the issue is acquiring label data, because this is usually very hard, right, for different reasons. And yes, there's a lot of work going on in the remote sensing community to cope with this, because very often we are in the situation that we either have few high quality labels or a lot of bad labels, like coarse resolution or outdated or slightly misaligned, right, syntaxes. And there are quite some approaches or also research efforts still going on to cope with this. Trying to adapt self-supervised learning methods, for example, borrowed from general computer vision, but also weakly supervised approaches or semi-supervised approaches. So there is a lot of research going on, a little bit still like borrowing stuff only from the computer vision community and applying it to the remote sensing data. But slowly we are also getting there that the field is more mature and we are developing methods that are specialized to the data we are actually working with. I hope that answered your question.
Thank you very much, Ronnie. Maybe we can go for one more question and then we can continue with the presentations. About the label problem, has one tried to apply deep reinforcement learning, e.g. the reward function aims at detecting clusters in the pixel feature space for each class?
Oh, that's a very precise question. So I think in general, most of the methods available in machine learning computer vision has been tried to be applied to remote sensing data in one way or another. So if this was at some point successful in computer vision, then I'm pretty sure there's also a remote sensing paper that tried that out. In general, though, at least to my knowledge, reinforcement learning is not a very common approach in the semantic analysis or even of remote sensing data, or even if we go for like geophysical properties. It's seldomly done because the supervision signal you have there is too weak, and it's not that easy to simulate. So if you do reinforcement learning in computer vision approaches, you usually do this in scenarios where you can run a couple of hundreds or thousands simulations in parallel. So and then you accumulate that. If you just have a real physical agent, like one robot that has to do reinforcement learning, usually you don't do it there. Maybe if you have like hundreds of robots that are doing that and then you accumulate, then you do this. And in remote sensing, we barely can do this. So I have not seen too many approaches with respect to that.
Thank you very much, Ronnie.
My pleasure.
Naoto, would you like to continue?
Sure. Let me share the slide. Okay, so I hope you can see my slide. I'm Naoto, a lecturer at the University of Tokyo and also a unit leader at RIKEN AIP. So today I would like to shortly talk about how to deal with the lack of training data in Earth observation, which is already mentioned by Petran and Ronnie as one of the major challenges in this domain. So I would like to introduce two examples. The time is limited, so just two examples. One of them is, let's use what we already have. So it's a kind of learning from weak supervision, which is already mentioned by Petran and Ronnie. So we already have some sort of GIS data. For example, OpenStreetMap is open map information. And also there are map products made from coarse or medium resolution satellite imagery, which is not perfect, but better than nothing if we do not have enough labels. And another approach is to, let's generate what we want. So if we don't have data, and if we can somehow generate them. So for instance, if we have any numerical models to simulate what we want to predict, we can use numerical simulation to create data. And also we can think about applying generative models to synthesize the data to increase the volume of data. So it's more related to learning from synthetic data or some domain adaptation to fill the domain gap. But the concept is to, let's create the data. So let me start from the first one, which is already mentioned by Petran. So I and actually Ronnie and Petran, we all together organized international data science competition, which is called IEEE GLSS Data Fusion Contest. And this year and last year, The topic was focused on land cover mapping, which is a semantic segmentation with weak supervision. For example, last year, the task was to classify every single pixel at 1 meter ground sampling distance using radar image and also optical imagery, using coarse resolution labels, as shown on the right-hand side. So actually, we have this kind of coarse resolution at 500 meter ground sampling distance. So each pixel is approximately spacing around 500 meter. So we already have the global semantic segmentation map for the whole globe. So why not to use such labels to create a high resolution classification map? So here, high resolution, we mean with the 10 meter. So try to use this kind of coarse resolution. And this is not only coarse resolution, but quite noisy. So include a lot of noise, label noise. And as a follow-up of the last year's competition, this year, we also organized the change detection competition, so semantic change detection. So the task was a bit different, but the concept is quite similar. So let's use 30 meter resolution labels for training and try to create land cover map at 1 meter in order to detect what kind of land cover change to what kind of land cover. So some examples are shown on the right-hand side, and examples of input imagery and also medium resolution labels are shown on the left-hand side. So this kind of task is related to learning from noisy labels or learning from aggregated information. So those, I think those topics are also actively studied in machine learning community, and this is really important in our applications. So another example is, let's create the data if there is no data. Let me explain through just one example. So I'm from Japan, and this Japan is suffering from a lot of different types of disasters. And this is an example of 2 years ago, there was a big typhoon, and this is optical imagery before disaster, and this is after the disaster. So usually it's covered by cloud, and usually if it's covered by cloud, we cannot see the ground. So in this case, we need to use radar image, which we can acquire images under any weather condition. So this is the pre-disaster radar image, and this one is the post-disaster SAR imagery. You can see that some pixels get darker, and actually, if there is no elevated objects, backscattering signal decreases, so it becomes darker. But in urban area where there are many elevated objects, backscattering becomes rather stronger. So if we make a color composite image, it looks like this. So we assign pre and post disaster images for RGB. So those colorful pixels indicate some existence of water. And by performing simple image processing, actually we can detect flooded region. And this is a kind of quite basic map that we need to provide as a first initial disaster response. But this information is not enough, because when flooding happened, if the flooding was just 50 centimeters, so inundation depth was 50 centimeters or 3 meters, they mean totally different damages on the buildings. So we need to predict inundation depths. There is a classic approach, but our approach was based on numerical simulation and machine learning. So actually, it was first time to apply a deep learning approach to the radar image to predict inundation depths as in through the real disaster response. And of course, there is an agency responsible for disaster management. They publish inundation depths. This is shown on the right-hand side. And this map is based on visual interpretation of aerial photo. So humans interpret the aerial photo and then use this flood detection map together with digital elevation model to estimate inundation depths. And our approach could output something consistent with what was done by humans. So it shows quite good potential to speed up the disaster response and to provide information that people needed during the disaster response. And let me explain what is behind this. So remote sensing is just observing what this is just observation, and by analyzing image, we can estimate which pixels were changed. But usually it's include false positive or false negatives, and it's not so easy to estimate, for example, inundation depths or when debris flow happen. It's not easy to estimate topographic deformation. So on the other hand, there are some numerical simulation people who have some simulation numerical models to simulate debris flow or flooding. So if we set up some parameters or input, we can simulate something. And of course, we can link binary change information and more detailed information like inundation depths and topographic deformation. By changing parameters or input, we can simulate many different cases, but also it's not that easy to get accurate input and parameters very quickly. So it really takes time to tune everything to fit the simulation to the reality. But we found that this simulation data could be used for the training data to build up the inverse model to predict inundation depths and topographic deformation. So the idea is, so those topographic deformation or maximum water level, it's really hard to collect such training data by field survey. So numerical simulation can be used to create such data. So once we build up this inverse model, we can just apply this model to the image analysis result. So this is the main idea behind what I introduced in the inundation depth estimation. So here are some examples for debris flows. So conventional approaches were limited to those results shown at the middle, and by using synthetic data, we can predict where the soil eroded and where the soil deposit. So lastly, I would like to introduce a bit about how to create images. So, which is a hot topic in computer vision. So maybe some of you wondered in this slide, So in this slide, if we can synthesize remote sensing imagery, maybe we can get rid of this binary change information layer. So that was our motivation. So if we know digital elevation model, which is kind of depth information from the sky, and label information, and now we can synthesize this kind of quite realistic optical imagery. So this is actually fake image. It looks good, but fake image. And this is the original RGB imagery. And by manipulating those DEM and label information, as shown on the right-hand side at the top. So here we just increase forest and get rid of some man-made objects, and then the generative model can create the corresponding very realistic imagery. So image synthesis from labels is quite common, but we also use them because if we just use label information, as you can see on the right-hand side bottom, the diversity of the buildings are not that great. So more information we use as a condition, better images we can get. So generative models can be used to manipulate the images and synthesize some images even which do not exist in this world. So here are more examples. So actually, third row is the synthesized images, and the last row is the real images. For RGB, and this is for radar. Honestly speaking, I cannot discriminate which one is real and which one is synthesized for the radar image. And this is an example. Just we just manipulate the elevation and semantic labels, just increase the sea level. And then you can see the synthesized images shows the more and more water regions. So this is a simple example, but we are planning to apply this kind of generative models to increase the number of images and introduce more diversity, something like seasons or some observation conditions and so on, in order to augment the image, so which might be helpful to deal with lack of training data. Yeah, from my side, that's all. Thank you.
Thank you very much, Naoto. Thanks a lot. I do see some questions related to your part here, but I need to find them first. So I'm interested in working on wildfires, but all the labels I can usually get are based on BAI or NBR. How can I find out whether my methods are usually better if I only have these labels?
Sorry, could you repeat again? It's related to wildfire?
Yes.
So you have only what? Sorry,
Sure. I'm interested in working on wildfires, but all the labels I can usually get are based on BAI or NBR. How can I find out whether my methods are actually better if I only have these labels?
Sorry, maybe I couldn't fully get the question. VAI. So wildfire is, I would say, it's wildfire detection is, to my experience, it's relatively easy if we can use some thermal imagery, or if we can have some optical imagery, including short wavelengths, which is we usually call a SWIR range, which is also sensitive to the temperature. But if we have thermal imagery, definitely we can. It's not that difficult to get quite highly accurate detection map. So I'm not sure what kind of input data he or she is using, but I think together with experts and using proper data, I think you can create quite precise label data, which can be used for the precise evaluation.
Thank you very much, Naoto. Well, actually, this partially answers Mishai's question as well. You know, in the remote sensing community, we of course have a lot of benchmark data sets. And for example, IEEE Image Analysis and Data Fusion Technical Committee are producing more and more benchmark data sets and organize more and more competitions based on those benchmark data sets. But the type of the data is completely different. So we have different types of data and we have different types of applications. So we cannot validate, for example, one particular deep learning based approach for which works, for example, for one data set, and then we can generalize it to other types of data. So for example, most of the approaches which have been developed, for example, for RGB images is not applicable to hyperspectral images because of the curse of dimensionality. So yes, of course, we have a lot of benchmark data sets in the community. And for some particular applications, for example, wildfire, for example, as mentioned here, maybe we don't have any particular benchmark data sets. So hopefully in the near future, we can have more data sets specifically related to different types of applications. And one of the activities that we followed in IEEE Image Analysis and Data Fusion Technical Committee was that we noticed that we have a lot of data, but those data sets have been saved in different data repositories, for example. Each of those data sets have been uploaded in a personal website, for example. So one of the activities that we are following now is to develop a database in which people can find different types of benchmark data sets with respect to their applications, with respect to the data that's used to produce those data sets, and with respect to geolocations. But it's an ongoing project, and I believe we will soon have this database running. So Ronnie, would you like to provide some more information about this database, EOD?
Sure. So one problem with remote sensing is that we do have a lot of different sensors available, and we have also a lot of different tasks we are interested in, right? So the combination between input and output is really, really big. And there is a lot of data available in the remote sensing community, but usually it lies on some kind of like private servers, like one university group was providing some data, or maybe like we as a technical committee from GSS are making a benchmark, but there is no general place to really search this, right? So the idea was that we create a catalog where you make all of those data searchable. So you display them on a map, you attach attributes to them, like what kind of sensory data is there, what is the geolocation, what is the nature of the reference data that is available. So we tried to put all of this into a catalog, and then this catalog you can just interactively browse. So you can like look through everything, you can sort it, you can filter it, you can display it on the map. So this is from the user's perspective. If you're looking for a specific benchmark data set at a specific location, for example, for a specific task, then you can just go there. And if you're a data provider, so you actually have created such a benchmark data set, you can also go there and just enter it to the catalog. So it's not just us who is putting our data there. It's meant for the whole community, that they can update this catalog on whenever new data is available, while the data itself is hosted somewhere else. So this is really just like hosting the meta information of this data. This is hopefully coming online in a month, and then hopefully this will push the community a little bit forward.
Thank you very much, Ronnie. So,
Pedro, sorry, I just read the chat, and I got the point of the question.
Sure, please go ahead.
I think the question was about, so if the reference is based on a simple model or simple method, how we can evaluate the performance of the new method, right? So my answer would be, if the reference is really fully based on the simple method, we cannot evaluate. We can just evaluate whether machine learning based approach can reproduce the result of the simple method. So if we really want to evaluate precisely, we really need help of expert or field survey to get more precise reference data. Yeah.
Thank you very much, Naoto. So I think we can proceed with Fabio's talk as well. Fabio, would you like to continue?
Yeah, sure. Let me share my slides. Okay, can you see my slides?
Yes.
Perfect.
Yeah.
Okay, thanks for the introduction earlier, Pedram. I'm excited to be here. So what are we going to be talking about today? I would like to cover a few topics. I would like to talk about why GUI is difficult, and I would like to give a little bit more perspective, especially from a data provider, on what are some of the issues that we are facing. Then I would like to talk about a little bit open science, open data, open standards, and I would like to bring up a couple of examples about, for example, SpaceNet and the work that the industry is doing towards a sort of standard called ARD, analysis ready data. And finally, I would like to talk about how GUI can be more impactful, especially talking about the SDG from the United Nations. So just want to give a little bit more perspective of why is it difficult. But first, I want to talk about what is Maxar. Maxar is a satellite operator, and we fly a constellation of 4 satellites. Ranging from 50 to 30 centimeter resolution. And in the next few months, we're going to be launching Worldview Legion, which is a constellation of 6 additional satellites with 8 spectral bands in the range of 30 centimeter. And these additional satellites will allow us to revisit the same point on Earth about 15 times per day. So the amount of data that we will be collecting in the near future is huge. Let's go a little bit more into the detail about space hardware in general. So color consistency. Some satellites have 4 bands, other satellites have 8 bands. Some of those bands are wider, other are narrower. And depending on all those variabilities, you can see color shift between different sensors. So this is, for example, the same red as seen from two different platforms. Ronnie touched about atmospheric conditions. I just want to add that in general, atmospheric conditions are not uniform, and you can see the variability here in the A's in this image. So you really want to work on what's called surface reflectance, which basically removes the effects of the atmosphere, making the green in this field similar to the green in this field. And surface reflectance is generally not used very often for in machine learning application. It's often is one of those steps that people just oversee and just don't do it. But it's definitely fundamental, as it brings you to a physical space of what you're collecting. Another aspect is interesting is that often you might only get one band. You might only get the panchromatic band, which is just black and white. Often satellites are not calibrated, and so the radiometry you get from one satellite could be completely different from the same radiometry you might get to a different satellite. And this really goes, it's really counterintuitive, and it's not really seen in the in the classic computer vision field, where you generally use like 3 bands, and you're okay with that. Then you have tiny objects. So often you want to detect something is very small compared to the size of the image. And just because of that, approaches like, I don't know, YOLO, for example, will fail miserably. So you want to do something a little bit more tailored for remote sensing. Another aspect that I believe is really important is the fact that my screen is not progressing. Anyway, is the fact that you generally want to use surface reflectance to do all your applications. And let me see if I can restart. Pedram, can you see my slides?
So I can see the slide related to only one band. Yeah, it's
okay.
Good.
Perfect. It's progressed. Ooh, it crashed. Okay, let me open the PDF. Sorry about that. I will. Yeah, I will restart the PDF. Just one sec.
Yeah, it looks good.
Oh, perfect. So you're only on one band. If you go to the next one, thanks for the backup slides. So you can see that objects also affect what is called like BRDF, which is a property of the materials and the structure of the materials. So in this example, you can see there are some rooftops on the left image that is brighter compared to the same rooftop that is darker on the right image. And in both cases, the only thing that changed was this the viewing geometry of the satellite. And so within the same scene, you have objects that are darker in one case or brighter in the other case, and vice versa. And so those effects are really important when you want to try to model, for example, what is a building footprint. If you go to the next slide. So what I talk about so far is mostly just the spectral differences, but in general, you also have geometrical distortions. And what you see in these slides is that the satellite can collect images from different direction, and there was an animation here that it's missed now in the PDF. But when you do the orthorectification, buildings still lean in different directions. And even if you do an image alignment, you still see building lean in different directions. And so this really complicates, for example, the generation of labels, because one building in one image can be laying on the right side, and another image can be on the left side, or for example, could be the image could have been acquired on nadir, and so you are perfectly straight down. Next. In general, one thing that is important is also talking about the sensor altitude compared to the spatial resolution. And what you can see at 80 centimeter resolution is different from what you can see at 30 centimeter resolution. In this case, this car is completely not understandable up to maybe like 50 centimeter. And if you go to the next slide, we actually did an experiment where we did a bunch of simulation based on the resolution, and you can really see cars with some confidence if you are below 50 or 40 centimeter. And yeah, you can you are able to detect some cars at a lower resolution, but not with very high confidence. Anyway, if you go to the next couple of slides, I want to dive a little bit more what is that some of the industry is working on with some governments or not-for-profit organization. The first example I want to talk about is SpaceNet. If you go to the next 2-3 slides. SpaceNet is a consortium of, let me try to drive this presentation because it's yeah, yeah, next slide. It's a consortium of different companies. Can you go back to the previous one? And in particular, there are like several different companies, and we can also see some agencies, some government agencies, and a not-for-profit organizations such as GRSS. And SpaceNet has been around for about 5 years. Next slide. In general, you can see that we have run different competitions. They're mostly focus on mapping challenges, for example, building footprints or road extraction. And you can see a variety of different sensors, including from other provider, and also like SAR data. Next slide. In general, just some numbers. SpaceNet has about 110 different geography can we go to the next slide? Thanks. With about 11 million of building footprints, 20,000 kilometers of roads, and we put together about $350,000 worth of prizes, and there will be more than 3,000 submissions. And we release all 38 algorithms, and most of these is still online, and you can run some evaluation. All that runs on Topcoder. Next slide. This is so ARD is one of the standards. It's coming out from as a partnership between different companies and, for example, NASA, ESA, and it's generally understood as a deep stack of tiles or images. And those images are generally curated. Often they're 8-bit, 3 bands, and they're ready to be ingested into classic machine learning frameworks. There is still some debate of what is ARD and what's analysis ready means for many applications, but I see some consolidation, at least in the industry, where this application is geared towards AI. Next slide. Most of the reason is because there has been an evolution in the usage of the imagery. Can you go to the next slide, please? So we range from just collecting an image of a parking lot to extract information out of it. And this information is, for example, the number of cars in it. And then the next part of the evolution will be to actually provide insight. So someone doesn't need to have the remote sensing image, can just extract a report where we see, hey, in front of the parking lot, there were 500 cars. And so the grocery store, for example, will have more revenue compared to last year. So that's the kind of evolution. Next slide. And another application is, for example, running analytics at scale. So combining the huge amount of satellite imagery that the industry and governments will be collecting in the near future, we'll be able to extract the pulse of the human geography. For example, in this example, we see how many cars are crossing the border in Texas, and we can just get a report that say 175 cars passed the border compared to 315 in November compared to August. So that is where we're heading, with the usage of ARD. If you go to the next couple of slides, I'm going to be talking about the SDGs. So those are the Sustainable Development Goals of the United Nations. There are 17 goals, and they cover different aspects. For example, no poverty, zero hunger, climate action, clean water, sustainability. All those comes with specific targets, and governments need to be able to measure those targets. And so this is where, in general, GeoAI can really play a huge factor, because it's a measurement that can be trusted by government to measure their progress towards those SDGs. If you go to the next slide, I have a few examples of how GeoAI can be applied. Next slide is actually an example from the flood in Germany and Central Europe from last week, where can really relate to number 13, which calls for climate action. And if you've seen the news, you've probably seen many of those images, either collecting from optical or SAR data. If you go to the next slide, number 2 focuses on zero hunger. And one application is to rethink how people grow different crops. And for example, in this image, a satellite image was used to do field segmentation. Next slide. Number 15 calls for for the attention towards maintaining the biodiversity of life and land and reducing the environmental degradation. And one application is, for example, counting trees within a neighborhood. In this case, again, AI was used to count trees. If you go to the next slide, number 7 called for access to affordable and clean energy. And so solar panel detection is it's a relatively easy task when you use 50 to 30 centimeter resolution. You can definitely see and detect solar panels on not only on those huge solar farms, but also on individual houses. If you go to the next slides, I only have a couple more examples. Those are examples where you can actually touch 2 different SDGs, in particular the health and well-being and reducing inequality, where GeoAI can be used for map population density and vaccine distribution. And this experiment, this project was done in 2019, so it doesn't have to do anything with COVID in general. It was more meant towards Ebola and eradicating some of those disease in Africa. Go to the next slide, please. This is another example where using GeoAI, you can capture a couple of different SDGs. In particular, no poverty and access to clean water. And those are refugee camps. The red and blue big structure on the left image are administrative buildings, and all the others are tent shelters. And you can see on the right side of the image, there are a lot of tents and shelters. Those are commercial people are trying to sell stuff at the refugee camp. On the right side of on the right image, instead, there is another refugee camp in Congo, and there is a mapping between boreholes and tents. So access to water is another thing. It's really important to map, and that's another place, another use set where GeoAI can play a fundamental role. That's it from me. Thanks for driving those slides.
Thank you very much, Fabio. So there is already one question for you. Will a SpaceNet challenge be organized in 2021 or 2022?
Yes, we are working with all the partners. We are in the process of reorganize SpaceNet, because we're adding new partners, and so in the near future, if it's not 2021, it's going to be definitely 2022.
Thank you very much. So yeah, okay. So Fabio, I have a question from you. How will providers of commercial satellite imagery contribute or steer the construction of training data in the future?
Well, definitely, there are different providers, both commercial and government providers, and Ronnie touched on this earlier. There is not really a standard. The JPEG 2000, JPEG, PNGs, TIFF, GeoTIFF, cloud optimized GeoTIFF. They're all different flavors of the same thing. One way where different people in the industry have tried to steer these is the adoption of that ARD standard, where everything will be providing a cloud optimized GeoTIFF. Everything will be on the cloud, and those styles should follow some definition. Except, for example, they all are 8-bit tiles in general, and they're all 3 bands. So they're all try to address the AI needs and the usability of framework that are borrowed from other communities. That's one way. Definitely, there are many more ways. SpaceNet is a good example, for example, to create labels. That's another way where the industry is trying to get together and try to steer the community and create like labels.
Thank you very much, Fabio. Thank you. So is there any questions that we missed? We try to answer all those questions through the chat box as well. But if there is any question that we missed, please let us know. And what about Python? So in order to answer your question, incredible joy. So there are, so if you want to stick to hyperspectral images, there are already quite a bit of libraries, either in MATLAB or Python, which are available in the community. For example, there are libraries dedicated to denoising or resolution enhancement, for example, or in particular classification or the fusion of hyperspectral with any other types of modalities. So there are many codes available for that, but unfortunately I don't have any link to them right now. But if you want, you can send an email to me and I can provide you with some codes. And so any more questions? Fabio, maybe I can ask another questions. So I completely agree with you. So when it comes to applications, I think sustainable development goals, or SDGs, which are defined by the United Nations, has quite a bit of potential to make the most of AI and EO at the same time to solve some of those challenges, to approach some of those targets. In your opinion, how we can connect AI and RS to solve those goals or to approach those goals?
Well, I think, first of all, I don't know if remote sensing will be able to solve the goals, but I think we will be able to create metrics to see at least how those goals have been addressed. For example, accessible, measuring the accessible water. It's something that remote sensing can easily see, and we can measure how progress has been done. Or, for example, counting trees or planting new trees. That's something that I feel that's where GeoAI can really help a lot. Not only government, but also NGOs and other groups are working towards addressing some of those challenges. And also like to think, out of the box. I constantly see, especially here in the AI field, I constantly see land use, land cover, or things like that. Think out of the box. There are so many more applications that don't really just focus on land use, land cover, and I think we should try to address those as well.
A good point, Fabio. Thank you very much. So I think there is no question left with no answers here, or maybe there is one. Which role, which role does RS have for the Green New Deal in EU?
Which SDGs? Well, let me see. Definitely life on land. That's one of the most important for the Green New Deal. You want to, make sure that life is sustainable. But all of those kind of like touch that. If you go to the UN website, there is a clear definition what some of those goals are and what they address, and so in each of them you can find some pieces of that. That's why I think it's really important to see all those goals as a whole and try to address more goal within the same task. For example, improving quality of life and access to water, they kind of like go together, in my opinion, especially in many less developed countries.
Thank you very much, Fabio. There is one more question. Very interesting points for the NGOs and their role in SDGs, Fabio, especially the contribution, the continuous learning. I think it is SDG 6, but not sure. Yeah, so it was more like a comment. So I'm very interested in the research related to the SDGs. For impactful research, it is important to have partnerships that are in the field. How can we approach these partners to help them?
As is for me. So I would say that almost every data provider, that this could be commercial or government, they're working with partners on addressing some of those SDGs. So if you're interested, reach out. We can definitely get you in touch with people that might be on the field. There are many NGOs working, for example, to clean up the ocean, and that's just one example. And definitely, I think one thing that I really like about GRSS in general, IEEE, is that it's a network of professionals working towards the same, the same goal. And through this network, you can get in touch with people in the field, with data provider, with AI practitioner, and it's the entire community that will help us, measure and eventually address the SDGs. And I totally agree with that comment that, in my opinion, research should be impactful. And I'm not very excited every time I see another land use land cover paper in the in the literature. I think we have the expertise to move on from there and try to address some of those issues that impact people.
Thank you very much. We already approached 17:15, so it means that this is the end of this session. So I would like to appreciate every and each of you for your participation, for your questions, and I would like to thank Fabio, Ronnie, and Noto for their very interesting talks. And I would also like to appreciate IEEE GRSS and E-Ray for making this fireside chat happen. Thank you very much and all the best. So one more thing, we have so E-Ray has a booth at ICML. So if you have any further questions, please don't hesitate to approach and ask your questions there as well. We will be very happy to answer your questions. Thank you very much. So all the best. Ciao.
Thank you. Bye-bye.
Thanks.